Then let's take a look. What is the process of communication? This will involve the name of a message. What is the name of this message? We can take a look. First, for the sender. We won't talk about the 7th floor, the 6th floor and the 5th floor. When our data passes through our 4 layers, that is, after the encapsulation of the transport layer, this data is called a segment. To our 3rd floor, the header that encapsulates what we call the network layer. We call it packets. This is what everyone means by sending a package and sending a package. The delivery process of the delivery package. In fact, it refers to the 3-layer data packet. To our current layer 2 data link layer. If we carry out 2-layer head and tail encapsulation, we call it frames. Then the frame, packet, and segment respectively refer to. We are just the name of the data on the 4th layer, the 3rd layer and the 2nd layer. You don't need to say this. What's the difference between them? There is no difference. Can you understand? No difference. It's just that each layer has a different name. The 4th layer is equipped with a 4-layer header segment. 3 layers are loaded with 3 layers called bags. The 2nd layer is called the frame. When the 2nd layer is installed, the head and tail are called frames. We will also decapsulate in the future. So its fundamental meaning is later. When we talk about a data frame, you have to know that we are referring to the 2nd layer concept. When it comes to the bag, it's 3 layers. Speaking of paragraphs, it's 4 layers. Sometimes when you look at documents, there will be some names like this. Each layer exists independently. The headers of each layer exist independently, but they are ultimately packaged in one piece. What we finally encapsulated is the complete classmates. It is not that it is completely encapsulated by several kinds of data. Is a complete overall data frame, packaged together, are added forward together, but they are really separated. We go down. Let's start with the transport layer. For the transport layer, we just mentioned the concept of a port number. For example, this is my local sender. For example, this is the opposite end. It writes a destination port here is 80. This means that we are accessing the HTTP service of the peer. It uses TCP port 80. That is, if you see the default port in the future, the destination port is 80. So by default we are actually using TCP. Such a reliable transport mechanism. Transmission Control Protocol. It's an overall big agreement framework. Our HTTP protocol is one of them. We say that with the help of such an agreement framework. To generate an agreement using port 80. It's enough for everyone to understand. That is, for the transport layer. First of all, when we encapsulate data in the future, our 3rd floor, that is, we actually encapsulate 4 layers first. Everyone needs to know 567. Let's not talk about encapsulating 4 layers first. There is an S in my local area on the 4th floor. Source port. It's a randomly generated port on my local. A random port. What does the random port mean? That is, we are randomly a port greater than 1024. Everyone understands this. Because we put 0 to 1024. We call such a port. They call it a well-known port. That is, we put the world. More ports used. For example, the following FTP, HTTP. Such ports are called well-known ports. Then, by default we put less than 1024. all less than or equal to 1024, are already equivalent to. You can't do arbitrary configuration anymore. They are some ports that we commonalize. We are admitting. You just say 80. It's the HTTP protocol. So when we go to the peer end locally, you have a port on the peer end. You must also have a local port. It uses 1027 here. I use my local port 1027 to access your peer. Assuming this is from a C company. Port 80 of company C's server. Can you understand? Port 80 of company C's server. Data sent to you. Then when you return the package to me in the future, the source and destination ports are to be swapped. Equivalent to when you send me now. The source is port 80. The destination is port 1027. So the equivalent of you are now on your local port 80 reply to port 1027 of my local device. Can you understand what I'm saying? That is us. The overall data communication is equivalent. If I have a port locally, I want to access another port of yours. When returning the package, you are also port back to port. This is our peer-to-peer reply relationship. So it's just a swap. This is our transport layer. Then the future port number is to distinguish our different network services throughout our CCNA curriculum. For example, we often mention HTTP 80, HTTPS 443, and we will often mention Telnet port 23. This is everyone in our agreement. We'll talk about remote login later. Then we log in remotely using Telnet. We are using port 23. This is what everyone needs to remember. You also need to recite. Basically, you don't have much to carry. There are some things I said to carry. You have to remember. Here are some of our transport layers. After the transport layer is sealed, we're going to the network layer. That is for the network layer. We have a little more to say. Let's take a look at it bit by bit. What is there for the network layer? For example, a basic IP header. First, let me tell you. I want to ask you a question. Since our data is encapsulated from top to bottom, we won't talk about the 7th floor, the 5th floor and the 6th floor. Let's default to 4-layer encapsulation. Everyone can see. What I am encapsulating now is an IP header. It's a protocol at our network layer. So it is equivalent to me that the 4 layers have been encapsulated now. This piece of data is called a data segment. We call it segment after 4 layers of encapsulation. Package is after the network layer header is encapsulated. Don't confuse this. But in fact, it is enough to understand. For 3 layers, there will be some parameters in the IP that are slightly more important. Everyone needs to remember. Let's look at the whole. I will pick a few important ones to talk about. First, here is a version. There are 2 versions of the IP protocol. One is version 4. The other is version 6. The version we use now by default is version 4. That's the IP address we're talking about now. The future will be IPv4 addresses. You will come to IE to learn version 6. Then the 2 sets of IP protocols of version 4 and version 6. In fact, its function implementation is very poor. Relatively speaking, the overall agreement concept, in addition to the overall framework design, is about the same. But the difference in function is a world of difference. But at this stage we are still using version 4. So we have to understand it as an header length. There will be a identifies our entire header length. Represents the length of our IP header. IP header is a variable header. Everyone can see. Here is a 20 byte. 1B equals 8 bit. Everyone should know about this conversion relationship. 8 is 8010100101. Binary code like this. This is called a. Our 8 binary bits are called a byte. So the length of our IP overall header. It has a fixed length of 20 bytes. There is an option behind. But it's basically useless. If options are added in the future, then it will take up some digits. Just understand this. DS field is a differentiated services. It has another name called DSCP. You will use it later when you learn IE. We don't need to pay attention to this thing at all in the NA stage. This is a total length. The total length represents IP header plus length of upper layer data. That is the total length after the network layer encapsulation. Some students will ask, isn't that the total length of the message now? Not really. Because we want to add the head and tail of the second layer. So actually the total length of the 3 layers here. I mean the middle. Also IP header plus upper layer data. This is enough to understand. Further down there is an ID number. A flax. A fragment offset. So let me briefly explain their concepts to you. We will mention something called sharding here later. When the data packet is transmitted on the link, the carrying capacity of the link is limited. For example, I want to send a data. Let's list it now. For example, here are a few devices in the middle of me. Draw some links between us. Then these links. Finally, the data message must be transmitted. Suppose I want to send an upper layer data now. The size of the upper layer data is 6 kilobytes. That for us. There will be a value on the link called MTU. That is the maximum size of data packets that a link can carry. By default, if we don't modify it, the MTU value on the link is 1500. Then this MTU. In fact, it is for our data packets. That is, the 3-layer packaging is completed. What we can carry by default is 1500. Then you said that now I have a 6000. Such a data. If I go directly from the link, can't move. It's like a bridge. A maximum of 1500 people can walk on this bridge. You now have to have 6000 people walking at the same time. Walk this bridge. That bridge can't carry it. You have to stand with so many people. The bridge is broken. But for our data communication, if you come over, you have to leave. Then you can't actually go. I won't send it to you. You can't get your data out at all. Now we have a method. We can divide this 6000 into 4 pieces. For example, divide it into 4 pieces of 1500. Then send it out 4 times. This is a sharding mechanism we are talking about. Can you understand? Equivalent to if the upper layer data is too large. We are at the network layer at this point. You can perform a slice of the data. Cut it into small pieces. Then divide the hair piece by piece. Then, for this sending process, it will have some doubts. We have to consider some problems in the sending process. For example, first question. I will give you an example. I have this device. The first device is sent to the 4th device. Suppose I am the 4th device. If in the future, I will provide services to a very large number of users. Every day a lot of data will be sent to me. So now the data you sent me. How could I know? This is the data sent to me by your device. You also send me more than one at a time. How do I know you sent me a set of data? Because now a lot of data is going from me. How do I differentiate this device? The 4 data you sent need an identification. You have to identify. The data you are sending now is a group. So before the future data is sent, divide the data into a slice locally. Add the same ID to it after sharding. This is called an ID number, equivalent to adding an identity. Let's say 4 ID numbers. Add a 100. Represent now. This is my device. Produces a set of sliced data. You need to know when you receive it later. This is what I sent you. And divided. Then for such a shard. In terms of our entire network layer now, what it uses is this identification. Identification by such an ID number. Identifies the future I, which is a set of data. It is good. This is point 1. 2 ND. We will now have another problem. I'm going to send you shards now. But after you receive this shard, how do you combine? Let's take an example. Like you posted a movie. This movie has a beginning, middle, climax, and end. How do you know which slice is on the head? Which one is at the end? Which one is in the middle? And you see I just now have device 1. My device 1 has been sending data to this device 4. I as a terminal. How do I know when you're done? I am a receiver device. You keep giving me ID numbers. Indeed I see you, this is a set of numbers. But when will you finish it? When do I start reorganizing here? How do I piece the data together? We still have a logo. Then in our whole, it will have a new function. Then in this function, it exists in this flags. There will be a shard. That is, there is a MF and a flag bit. Indicates whether there are any shards behind. If there is no fragmentation displayed in this, then the peer device can start to reorganize. Can you understand? The last has a slice offset. What does this mean? In the future we send data. Everybody needs to know. There will be an out-of-order problem. I send data. I send it to you once by 1234. But when you don't necessarily collect it, it's 1234. Data in the process of network transmission. There may be some out-of-order issues. There is some delay. Then what you finally receive may not be charged according to 1234. So now there's a feature to reassemble the received shards in order. Then there will be a number. Like what do you mean? We are still for the offset just now. Is it divided into 4 pieces? I can make the first block represent 1 to 1499. This is 1500. The second, from our 1500 to 2999. Do you understand me saying this? So take our 0 and 1500. Can be offset when we a shard. It's like starting with 0. And then 1500 starts. Further down, it starts with 3000. It is good. 3000 starts down. Further down is the beginning of 4500. Then mark everyone when you come over. You are this 0. That is, you are the first paragraph. You are this 1500 is the second paragraph. You are this 3000. You are the fourth paragraph of this 4500. Everyone needs to come. Indicate which segment of the entire data you are in. After reaching the opposite end. Since we have just discovered what kind of data is finally received. When to start restructuring. After receiving the last message. We can put it together like a puzzle. So this is a shard of our 3-layer it. Including that we can finally restructure. A mechanism for messages. Alright. Is our layer. I'll go on. Here's a time to live. What does this mean? For our 3-tier. It creates a loop problem in the future. Have you heard of the ring road? The future. What might happen to the data? during my entire data transfer. My message. Keep going in circles and circles in the web. But I just can't reach my destination. Then our TTL value. Time to live. It's about the future. How many 3-tier devices have I passed? In fact. Tell everyone. What is the TTL value that you are probably most familiar with? Is 255. In fact. 4 different manufacturers. Different series. Different models of equipment are not the same. 64, 128, 255. Not fixed here is 255. Tell everyone this. It's just that most of you see 255. So in the future, if here, for example, I am 255. Then every time I pass through a 3-layer device. In the future, I would decrement this value by 1. For example, now our network topology is like this. Engineers may have planned wrong. Then I generate a data in the future. I think go right. It also thinks go this way, go this way. Every time we check the routing table, it turns out that the data is always going to the right. This is very easy to appear when we configure unfamiliar routes. It's very easy for this to happen, including your future to the NP stage to learn OSPF. The loop problem is a very difficult problem to solve. Let's take a look. If it is said that a number is generated locally, my TTL value is 255. Then every time I pass a 3-layer device, I will subtract 1 locally. Reduced to 254. Here 253. Then 252, 251, 250. Turn around. Turn around. Go to the end. For example, the device received a TTL value equal to 1. In my local, 1 minus 1 equals 0. If I subtract it locally, it is equal to 0. I will throw this message away. It is equivalent to us passing the TTL value. Can temporarily prevent or suppress this round of loop problems in our network. It doesn't break the loop. It can only say to temporarily remove the loop. Once the next time you send this message again, I'll start turning again. Only. Finish 255 times. I'll throw this one away. This message will not be forwarded in the network all the time. That's all I can do. Let's go down and see that there is a protocol. What does the agreement mean? The protocol is the identification of the upper layer protocol. We identify services above the network layer. So suppose in the future we will learn a protocol called ICMP. By default it is a. If I fill in 1 in the protocol field on the 3rd floor, represents my upper layer is an ICMP. Everyone knows the employment of tracer. That is our trace ROS. In fact, it is our trace. It's all about our ping command. ICMP is based on the sending of one of its messages. This is the protocol. In the future we will also learn about UDP and TCP. Because the upper layer of our network layer is the encapsulation of the transport layer. The 2 major protocols of the transport layer. If it is TCP, here is 6. If UDP, here is 17. It's here if you fill in 17. It means that my upper layer is using the UDP protocol, sent to the next 3 floors. After dismantling, I will send it to the upper layer protocol for processing. Just send it directly to UDP for processing. In the future we will also learn an OSPF. It also works on top of the network layer. But it doesn't belong to the transport layer. We will talk about it later. Then the protocol number it identifies here will be 89. If it is 89, it means that the upper layer is now an OSPF protocol. It is used to identify the upper layer protocol. Alright. Let's go on. There will be a header checksum in our entire network layer. That is, the third layer also provides a verification function. Can verify the integrity of the three-layer data. Similar to the second floor. But the algorithm it uses is called 2's complement summation. Not the same as layer 2 CRC. But it is also possible to check the integrity of the header. This is enough to understand. Know that it has an integrity check function. It can also be checked. Next we compare the important parameters. Called source IP address. A called destination IP address. These are the two key parameters of our three layers. Must remember. We will have source and destination IP. When we encapsulate at 3 layers. It's like when we encapsulate 4 layers. There will be the same source and destination ports. You must remember the most core parameters of each layer. Layer 4 source and destination ports are its core. Layer 3 source and destination IP is its core. This is our layer 3 source and destination IP. We go down. Not to mention this option. Because basically we can't see it. Unuseful. Including learning IE stage. We rarely use this option. In the future, the source and destination IP will be the time when the data is sent. My IP and peer IP. Say 2 devices. I am 1.1.1.1. It is 1.1.1.2. Then I am here. The peer is 1.1.1.2. We send a data for data communication. This is a piece of data that the network layer encapsulates. Let's go down to the data link layer. For the data link layer, we will only cover one Ethernet LL. Let's just take a look here. For our data link, there is a frame header and a frame trailer. Then the middle. In fact, this passage is our packet. Also through all our. After several layers of packaging, we call it packet layer 2. Plus 2 layers of needles and true tails. This is called the data link layer. After adding, we call it a data frame. It's a name. Everyone needs to know first. Data link layer. There are actually 2 frame formats. Something called Ethernet LL. A type of 802.3 called IEEE. Here to tell you about IEEE 802.3. Another data encapsulation standard. For such a standard, we see less. We use more Ethernet LL. Its structure is also very simple. There will be a type. That in this type, we also identify the upper layer protocol. Everyone can see. If we choose 0800 in this, that is a hexadecimal number. Identify my upper layer data volume. What's on the 6th floor? Is it 3 floors? On behalf of the 3 layers we use the IP protocol. If now I am using 0x0806 here, identifying what our future upper layer will use is called ARP. This is for future data communication. An inevitable agreement. One that must be used in our Ethernet. Such an agreement. We'll cover that in the next lesson. When speaking of our real network communications. This agreement. It is an agreement that we must learn at the NA stage. We throughout the stage. In fact, whether it is learning VLAN or learn OSPF. In fact, I learned something else. Part of what we call technology. There is only one protocol like ARP. Is to require everyone to be in the NA stage. A protocol that must be fully mastered. So its status is very important. If you can fully understand it. In fact, even if we NA did not learn in vain. So the theoretical part of our first few lessons is important. I hope you can lay a solid foundation. This is our point. Ethernet LL. This is a form of encapsulation of our data link layer. There's another D.MAC here. This is our destination MAC address. AS.MAC. A source MAC. This side will identify the two core parameters. When our data is passed on the link layer. MAC address. Online. This type is to identify the upper layer protocol. Can you understand? You can see a date. This is data. Then you will also find that when each layer is encapsulated, we all have a data section. Then everyone will find what is actually marked in it. After our 5, 6, 7 layer encapsulation, it reaches the 4th layer. It will consider all the data above. All are called date. Can you understand? On the 4th floor, it will not look at the heads of the 5th, 6th, and 7th floors. This data is encapsulated to the 4th layer after 5, 6, or 7 layers. The 4th floor thinks that all the data is given to me. It's the same on our 3rd floor. I will not go to the 4th floor on the 3rd floor. I just think you're full of data. Only this one I encapsulated is called the header. The same goes for the 2nd floor. After a few layers of encapsulation above us, I don't see which one is the head. I think it's all called data. Only what I encapsulate is called frame header and frame trailer. That is, the lower layer does not pay attention to what encapsulation the upper layer has undergone. I only know that you have reached my level. I want to perform encapsulation. Nothing more. So for the upper layer, this is called data. Then our packet actually appear at this location. Then this type. Of course, it is in the encapsulation of our data link layer. This is our type. A piece of data that identifies the upper layer. Further down is the MAC address of the Ethernet. For our current MAC address, it will have an allocation criteria. The definition of allocation criteria is also very simple. Let's look first. It is divided into first 24 bits and last 24 bits. The two 24 bits are specified separately by our various suppliers and different products from suppliers. We briefly introduce. For us now, the first 24 bits are made by us, a management organization such as the overall IEEE, assigned to each supplier. Suppliers are actually what we call vendors. The top 24 1010 manufacturers are different. Then the last 24 bits are determined by the vendor. That is, the manufacturer allocates. For example, switches, routers, firewalls, wireless devices. In the end, they all use numbers that start with. Different manufacturers have different standards. Then our entire MAC address. A total of 48 bits of address space. MAC address. First of all, it will not have the problem of exhaustion. It won't run out. Second, even if everyone is worried, there will be a day when you will run out of MAC addresses. That doesn't matter, because our device will have virtual MAC in the future. That is, for our manufacturers, our device can still have a virtual MAC address to use. So the MAC address can be sure. Each of our network cards, the MAC address that comes out is unique in the world. So you don't need to worry about this. That means MAC address. In the future, it can be used as our single device. Real identity. So we call it physical address. That's what it means. And our IP address can only be called a logical address, because IP addresses can be configured repeatedly. This is our MAC address. Then let's go down. We're going to touch on a concept in our second floor. Everyone can see. In layer 2 frame we will have 48 bits. What is the number 48 called? It refers to 48 binary codes such as 010101. If the future destination MAC. We are a 7th bit 0. Such a MAC address. Prove that we are communicating unicast. Unicast is called one-to-one data communication. I am going to host PC host 1 now. To send a data to the host separately. Then in the future I send a MAC address. It's called a unicast MAC address. We call this a unicast MAC. A protocol we will learn later. ARP protocol. It uses broadcast on our second floor. Our future purpose MAC. Our 48-bit binary full system is 1. Then we call it broadcasting. Here it is written as 12F. We say 48 ones are 12 16s. So you sometimes see all F. In fact, it represents 48 1s. It involves a base conversion relationship. Leave you a homework. Go back and have a look at binary, decimal and hexadecimal conversion. It's called broadcasting. If the destination MAC is all 1, we are a radio. The last one is multicast. Multicast will involve a destination MAC here. If bit 8 of the destination MAC is 1, then the representative is now a multicast MAC. Multicast communication. First, let's talk about multicast communication. This is the part you will learn in your IE course. Then it doesn't affect us to touch it in NA. What is multicast? For example, in the future we will learn a protocol called OSPF when learning OSPF. Everyone knows its overall maintenance. Or build a neighbor relationship. We make general announcements. We are all using multicast. Is using a multicast address. A multicast address such as 24.0.0.5. Our MAC in the second layer will also have a corresponding MAC address. If you are interested, you can check it out in private. But I usually remember 3 layers. For our second floor. What does such a multicast mean? For example, now ABD has added a group. Like they run an OSPF. It is equivalent to 3 of them will write a question. But this host C will not write. You can understand it this way. Everybody knows. Generally great people like to play with great people. If you are, possibly the nature or talent is not high. You can't participate in discussions in our group. That's what it means. When we communicate on a daily basis. Although my data is also. The whole circuit transmits. But you don't receive this item. Someone else ran OSPF. You ran a RIP yourself. Then you can't exchange information with each other. Can you understand? Multicast is equivalent to adding a group. They will only receive within range. And the broadcast we just talked about. Broadcast is as long as I'm in the same broadcast domain. I send a broadcast data. All are acceptable. We call it one-to-many. But broadcasting is called one-to-all. Multicast is called one-to-many. It has a concept of group division. But the division of groups is based on our future IGMP protocol. You will learn this in IE. It will have a concept of adding groups during this NA process. Just remember, multicast its address with bit 8 of 1. And multicast has an add group. That's all, it's okay. This is our lesson content today. Today, talked about the encapsulation of our overall reference model. From the next class, we're going to start talking about layer 3 IP addresses. IP address, division of company network addresses, and the encoding format conversion of IP address, subnetting, etc. Now I will answer your questions. All kinds of knowledge. About the encapsulation header in the network layer. Is it important? It's not very important at this stage. But you have to lay the foundation first. You have to know it's in 3 layers. What kind of encapsulation does it perform? The requirements for everyone in the NA stage are: after you finish these lessons, basics to know. Overall class hours in our NA. Actually more involved. Is a conceptual understanding of a network. So no matter the configuration. Conceptual understanding is also very simple. Everyone just knows that there is such a thing. You don't need to interpret in detail. Each field inside. Encapsulation and decapsulation are important. But I can tell you. Not every field in it is useful. This is okay. Tell you clearly. Because for example in the IP layer. The role of each field in each layer. In the end, you may not all learn. Can't use it at work. Can you understand? And many fields in IPv4. It's already obsolete technology. On the basis of the present. The outlook for the future stage involving IPv4. In fact, IPv6 can achieve. So now a lot of expanded content. No need for IPv4 at all. So you don't have to go too much tangle about its optional part. This is what we say. 2. Is encapsulation and decapsulation important in the NA stage? Of course it's important. But you don't need to go into in-depth research for each field. There is no need to look at each field to capture packets. In fact, as you learn, slowly you understand. Actually, it's not that difficult. No need to back. What you need to remember now. The first is the name of each layer. And the focus of our layers. When it comes to layer 2, you need to know MAC and error detection. When it comes to layer 3, you need to know IP and routing. It's okay to know a port on the 4th floor. Let me emphasize again. Of course, you can have higher demands on yourselves. For example, each field. We all have to figure out what it means. But we do not require it in the teaching of the course. Each student has their own way of learning. It's not that the more meticulous the study, the more things you carry, the better. Learning is more importantly a process of self-exploration and exploration. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMO Education. I'm Grolin Annesley from ThinkMO. I hope today's content is helpful to you. See you next class. Bye classmates.